Hello students. In today's presentation, we will study about the work done by a variable force. A constant force is very rare, but the variable force is very commonly encountered. In section 6.6, we will study about the work energy theorem, which is useful in solving many problems. In section 6.7, the concept of potential energy, which is related to the capacity to do work or stored energy, will be explained. Finally, in section 6.8, the conservation of energy will deal with the work done in a closed loop. All these sections are very important. Please note down and make your own notes. I welcome you once again. Work done by a variable force. As said earlier, a constant force is very rare, whereas the variable force is more commonly encountered. To understand this concept, please refer to the diagram A on the right hand side. Here, a graph is plotted in the x-axis. It is the position. Xi is the initial position and Xf is the final position. So along the x-axis, the difference between Xf and Xi is the displacement. The force, applied force, is plotted in the y-axis. So Fx is in the y-axis, and for example, this is a curve, the force, and this curve is divided into a small strips or the small areas. So figure here shows the plot of varying force. This is a variable force in one dimension. If delta x, that is the rectangular position, delta x is small, we can take the force Fx as approximately constant, and the total work done is Fx f of x into delta x. So the relationship, the work done delta W is equal to Fx, which is a force, and delta x is the displacement, which is shown in the figure. Adding successive rectangular areas in figure A, we get the total work done as summation of initial position to final position, that is sigma of xi to xf of fx into delta x. Therefore, if the displacements are allowed to approach 0, that is as the delta x tends to 0, the number of terms in the sum increases without limit. But the sum approaches a definite value equal to the area, underline area under the curve figure B. So the same thing is plotted in the curve B here, and the total displacement is taken between xi and xf, and the plot is represent the work. So therefore work W is equal to limit of delta x tending to 0 of summation sigma xi to xf of fx delta x. Therefore, that this can also be removing the limit represented as integral xi to xf of fx dx. You will learn about definite integrals in your mathematics class. For the time being, assume that limit of delta x tending to 0, sigma xi to xf of f of x dx can be represented as definite integral xi to xf of fx dx. Thus, for a varying force, the work done can be expressed as a definite integral of force over displacement. Next, we will take up a worked example on a work done by a variable force. In question number 5, it is given that a woman pushes a trunk on a railway platform which has a rough surface. She applies a force of 100 newtons over a distance of 10 meters. Thereafter, she gets progressively tired and her applied force reduces linearly with distance to 50 newtons. The total distance through which the trunk has been moved is 20 meters. So the question is, plot the force applied by the woman and the frictional force, which is 50 newtons versus the displacement. Calculate the work done by the two forces over 20 meters. Let us solve it. The plot of given problem is shown in the figure displayed before you. This plot has x-axis wherein we have marked displacement. So it starts, initial position is 0, that is A, and 10 meters and 20 meters are shown. So along the x-axis we have displacement. In the y-axis we will plot force. So the forces are given in y-axis. So the position A, point A has 0 newtons and point B has 100 newtons. So force is in newtons is plotted in y-axis. As given in the problem, the woman applies a force of 100 newtons initially from at point B and moves a distance of 10 meters up to point C. At the point C, she gets tired and reduces her force linearly. So it is a inclined line and getting reduced at point C to point E, where at point E we have the force gets reduced to 50 newtons. This is the plot of actual work done by the woman. So this figure and the frictional force which opposes the main force applied by the woman is minus 50 newtons, and it is shown in the negative y, minus y, that is F friction is minus 50 and the friction is constant all through up to 20 meters. This is the plot of the work done by the woman. That is plot of force versus displacement. This figure has three parts. First part is a rectangle BCDAB, that is 100 newtons up to 10 meters rectangle. And then the next part is CEIDC, which is a trapezium due to reduction of force from 100 newtons to 50 newtons. So this is a trapezium. And the force due to friction is in the negative axis, that is negative of y, minus y. Therefore it is minus 50 newtons up to 20 meters. So we have to know the area of the force versus displacement. So at x is equal to 20 meters, F is equal to 50 newtons, point E. At x is equal to 20, force is 50 newtons. Therefore, frictional force F is mod of F is equal to 50 newtons. It opposes the motion and acts in the direction opposite to F. It is therefore shown on the negative side of the force. The work done by woman is WF, that is equal to area of rectangle ABCDA plus area of trapezium CDIDC, or we can call CEIDC. Therefore, we have to calculate the areas. Area of rectangle is 100 by 10, 100 into 10, plus area of a trapezium is half into sum of parallel side, 100 plus 50 into 10. That is equal to, simplifying, we get 100 into 10 is 1000 plus half into 100 plus 50 into 10 is 750. So total is 1750 joules. The work done by the frictional force is the rectangular area AGHI. Therefore, frictional force WF is given by minus 50 into 20. That is equal to minus 1000 joules. Please note, we have used subscript capital F for work done by the force of woman and small f for the frictional area. The work energy theorem for a variable force. We know that the time rate of change of kinetic energy is given by the relation dk by dt is equal to d by dt of half mv square. Here we have used the relation capital K is equal to half mv square. Therefore, dk by dt equals d by dt of half mv square. Now we will integrate the right hand side. If we integrate, we get m is constant, that is mass. M is equal to d by dt of 2v square is d by dt into v. So 2 and 2 gets cancelled. Therefore, we can write m into dv by dt as f. That is, f is equal to ma from Newton's second law, and copy the v as the speed v as it is. Therefore, v can be written as f dx by dt. Therefore, right hand side is f into dx by dt. Thus, dk is equal to f into dx. Integrating this equation, we get integral ki to kf of dk is equal to integral of right hand side is f of xi to xf of f of dx. Here ki and kf are initial and final kinetic energies, and xi and xf are the final positions. So integrating, we get left hand side is equal to upper limit is kf minus lower limit ki equals right hand side is f of dx is work done. Therefore, this relation kf minus ki is equal to W is the work energy theorem for a variable force. Thus, we have proved work energy theorem for a variable force. Now we will quickly recapitulate the difference between Newton's second law and work energy theorem. Formula is, as we know, F is equal to m into a, that is mass into acceleration. And work energy theorem is integral of initial kinetic energy to final kinetic energy of dk. That is equal to, on the right hand side, x1 to xi, that is initial position to final position of force F into dx. Hence, the Newton's second law is a relation between force is equal to mass into acceleration, whereas work energy theorem is an integral of Newton's second law. The time in period applicable for Newton's second law is instantaneous time, whereas work energy theorem is for the time interval between initial and final position. Also, Newton's second law can be written in a vector form of 1, 2 or 3 dimensions, whereas work energy theorem is a scalar quantity. Let us solve a numerical example. Question number 6. A block of mass 1 kg moving on a horizontal surface with an initial speed of 2 meters per second enters a rough patch of x is equal to 0.1 meter to 2.101 meters. The retarding force Fr on the block in this range is inversely proportional to x over this range. So the relation is given as retarding force Fr is equal to minus k by x. Here this is a small k. The value of small k is 0.5. It is given. This relationship is applicable between 0.1 meter to 2.01 meters, and it is 0 for rest of the position, that is for x less than 0.1 meter as well as for x greater 2.01 meter, retarding force is 0. Here K is given as 0.5 joules. What is the question is, what is the final kinetic energy? We have to find the final speed of the block as it crosses this patch. So we have to find capital K suffix F and V suffix F. Let us do it. We know that the relationship between kinetic energy is given by integral Ki to Kf of dk is equal to final kinetic energy minus initial kinetic energy, that is equal to integral xi to xf of f of dx. So kf minus ki left hand side is equal to integral 0.1 to 2.01 of minus k by x of dx, because f is given as fr is given as minus k by x in the question. Therefore the kf is equal to Ki can be written as half mvi square minus integrating this term, that is integral of 0.1 to 2.1 is small k is a constant taken outside. So integral of 1 by x dx is natural log x between the limit 0.1 to 2.01. That can be written as half mvi square minus small k into natural log 2.01 divided by 0.1. We know that natural log x is given by 2.303 log of x to the base 10. So that can be written as half into mass is given as 1 kg, initial velocity is 2 meters per second square whole square minus k is 0.5 and natural log of 20, that is simplifying 2.01 by 0.1, 20.1. Therefore kf, the left term on the left hand side, is equal to 2 minus 1.5, that is equal to zero point 0.5 joules. We are also required to find the velocity, which is given by the relation Vf is equal to square root of 2 into kf divided by m. Therefore, V is equal to 2 into kf is we have calculated as 0.5 divided by 1, that is equal to 1 meters per second. The concept of potential energy. The word potential energy suggests possibility or capacity for action. The term potential energy brings to our mind the concept of stored energy. For example, a stretched bowstring possesses potential energy. When it is released, the arrow flies off at a greater speed. Another example of potential energy is fault lines. As we know, Earth's crust is not uniform but has discontinuities and dislocations that are called fault lines. These fault lines in the Earth's crust are like compressed springs. They possess a large amount of potential energy. An earthquake, whenever it results, these lines get readjusted. Thus, the potential energy is a stored energy by virtue of its possession or configuration of the body. The body left to itself releases this stored energy in the form of kinetic energy. Another example of potential energy is a ball raised to a height h. The gravitational force on this ball of mass m is given by mg. G may be treated as a constant near the Earth's surface. When we say near, we imply that height h of the ball above the Earth surface is very small compared to Earth radius. That is, h is far less than r, so that we can ignore the variation of g near Earth's surface. We can take upward direction as positive. Let us raise the ball to a height h. The work done by the external agency against the gravitational force is mgh. This work is stored as potential energy. The gravitational potential energy of this ball as a function of height is denoted by capital V of h, and its negative of the work done by gravitational force in raising the object to that height. So V of h can be written as V of h is equal to mgh, where V of h is the potential energy and m is the mass, g is the gravitational force, and h is the height. If h is taken as a variable, it is easily seen that the gravitational force F equals the negative of the derivative of V of h with respect to h. Thus, F is equal to minus of dV by dH. So dV by dH is the derivative. Here for reference we take V of h. Therefore, which is equal to, if we take the differential of V of h, it is minus mg. This negative sign indicates that the gravitational force is downward. When released, the ball comes down with an increasing speed. Just before it touches the ground, its speed is given by the kinematic relation, that is v square is equal to 2gh. This equation can also be written as half mv square is equal to mgh. That is, we multiply both LHS and RHS with m and shift this 2 to the denominator on the left hand side, which shows that the gravitational potential energy of the object at height h when the object is released manifests itself as kinetic energy of the body or the object on reaching the ground. Physically, the notion of potential energy is applicable only to the class of forces where work against the force gets stored up as energy. When the external constraints are removed, it manifests itself as kinetic energy. Mathematically, for simplicity, one dimension, the potential energy V of x is defined if the force Fx can be written as Fx is equal to minus dV by dx, which implies integral of xi to xf of Fx dx is equal to minus of Vi to Vf of dV V dV, that is Vi minus Vf. The work done by conservative force such as gravity depends on the initial and final positions only. If an object of mass m is released from rest from the top of a smooth and frictionless inclined plane of the height h, its speed at the bottom is square root of 2gh, irrespective of the angle of inclination. If the work done or the kinetic energy depends on the other factors such as velocity or path taken by the object, the force would be called a non-conservative force. Please note, if the kinetic energy depends on other factors such as velocity or path taken by the object, the force will be called non-conservative force. The dimensions of potential energy are ml square t to the power of minus 2. That is, for any energy, it is same, ml square minus t to the power of minus 2, and its unit is joules, capital J. Thus, the change in potential energy for a conservative force delta V equals minus of F of dx, that is negative of work done by the force. In section 6.8, we will study about the conservation of mechanical energy. Suppose a body undergoes a displacement delta x under the action of conservative force F. Then from work energy theorem we have delta k is equal to f of x into delta x, where delta k is the incremental kinetic energy, f of x is the force which is a function of displacement into delta x is the displacement. Therefore, if the force is conservative, the potential energy function Vx can be defined such that minus delta V is equal to f of x into delta x. Therefore, from equation 1 and 2, we get delta k plus delta V equal to 0, or delta of k plus V is equal to 0, which means that k plus V, that is kinetic energy plus what potential energy, the sum of kinetic and potential energies of a body is constant. Over the whole path xi to xf this means that ki plus v of xi equals kf plus v of xf, where ki is the kinetic energy in initial position and v of xi is the potential energy at the initial point, and kf is the kinetic energy at the final point, and v of xf is the potential energy at the final point. The quantity k plus Vx is called the total mechanical energy of the system. Individually, the kinetic energy k and potential energy V of x may vary from point to point, but their sum is constant. Some of the definitions of a conservative force. A force Fx is conservative if it can be derived from a scalar quantity Vx by using the relation minus of delta V is equal to f of x into delta x. The work done by the conservative force depends only on the endpoints. That is, the relation work W is equal to final kinetic energy Kf minus Ki. That is equal to V of Xi minus V of Xf. Please note, in the potential energy V, Xi comes first and Xf comes next because of the negativity. The work done by this force is in a closed path is 0. That is point number 3. This is apparent from the equation Ki plus V of Xi equals Kf plus V of Xf. since xi equals xf in a closed path. In a closed path, xi is equal to xf. Therefore, the statement we can summarize as the total mechanical energy of a system is conserved if the forces doing the work on it are conservative. Example: a ball of mass m is dropped from a height h. The total energy of the ball at different height as shown in the figure is, we have in the y-axis, that is x displacement is shown on the y-axis. So capital H is the height of a cliff where v is equal to speed is equal to 0 because body is at rest and it falls down from capital H, and at the ground v is equal to the speed is equal to vf, that is the final velocity or final speed. So we will calculate energies at 3 points, that is at the height capital H and in intermediate height small h and at the ground. So at EH, energy is potential energy, that is equal to mg into capital H, that is equation 1. In the intermediate position, that is at the height small h, EH small h is equal to mgh plus kinetic energy half into mvh square. Please note, at the height h, while the body is falling, there is both potential energy plus kinetic energy. Let it be equation 2. Then finally, at the ground level, E naught is equal to half mvf square. At the ground, there is only kinetic energy, that is half mvf square. Let it be equation 3. The constant force is a special case of spatially dependent force effects. Hence, the mechanical energy is conserved. That is, EH is equal to E naught. Therefore, mgh, EH is mgh, E naught is half mv square, or from this equation we can simplify Vf as Vf is equal to square root of 2gh, that is Vf is equal to m and m gets cancelled, 2gh and square root. We taking square root, we get Vf taking the square root. Then equating E capital H equals E of small h is equal to Vh square is equal to, if you put EH is equal to E capital H mgh is equal to mgh plus half mvh, we get 2g into Vh square is equal to 2g into h minus h, or V small h is equal to square root of 2g into h minus h. The concept of conservation of mechanical energy can be very well understood by considering an example of motion in a vertical plane given in question number 7. A bob of mass m is suspended by a light string of length L. It's imported a horizontal velocity v0 at the lowest point A such that it completes a semicircular trajectory in vertical plane, with the string becoming slack only on reaching the topmost point C as shown in the figure. Obtain an expression for v0 and speeds at point B and C. Finally, the ratio of kinetic energies, that is Kb ratio Kb to Kc at points B and C. Comment on the nature of the trajectory of the bob after it reaches point C. The question is given in the figure on the right hand side. Points A, B and C lie on the trajectory of the semicircular path in the vertical plane. L is the length of string, that is, this is center, and the length between the center and point A is L, capital L. Similarly, length OB also is L and OC is also length. It is constant. Length is constant. So we are required to find the velocity, the speeds, and the ratio of kinetic energy. So this system is acted upon by only two forces, that is due to weight, the gravitational pull due to weight, that is M into G, and the tension. There are no other forces, hence forces are conserved. Take the potential energy of the system at the lowest point A equal to 0. Here at this point A, the potential energy is 0 and C is the topmost point. Thus at point A, energy is equal to half mv naught square. Let it be equation 1. So here only kinetic energy is there, that is given by half mv naught square. Resolving the forces at point A, we get Ta minus mg. Ta acts vertically up, mg acts downwards, is equal to energy is given by mv naught square by L. That is from Newton's second law. Therefore, Ta minus mg is equal to m into v naught square by L, where Ta is the tension due to string at A. Similarly, at point C, we get E is equal to half mvc square plus 2 into mgl. That is, Vc is the velocity at point C. That is speed or velocity at point C. Speed because we are considering only a single dimension, one dimension. Therefore, we get mg is equal to mvc square by L from Newton's second law. Or mvc square is equal to mgl, or vc square is equal to g into L. Let it be equation 3. Therefore, from equation 2 and 3, we get E is equal to mgl, taking mgl common, half plus 2 into mgl. mgl is taken common. Therefore, E is equal to 5 by 2 mg into L. Equating this to energy at A, we get 5 by 2 mgl is equal to m by 2 into v naught square. So we have found energy at A as mv naught square by 2. Therefore, we get, solving for v naught, we get v naught is equal to 5 into g into L. Because m gets cancelled, 2 in the denominator also on the left side and right side get cancelled. Therefore, V naught is equal to square root of 5GL. Again, from equation 3, we get Vc is equal to square root of GL. In equation 3, Vc square is equal to GL. Therefore, Vc is equal to square root of GL. Therefore, at point B, energy is given by E is equal to kinetic energy half m into Vb square plus mgl, where Vb is the velocity at the point B. Equating this to energy and using equation V naught is equal to square root of 5gl, we get half of m into Vb square plus mgl equals, that is, energy at A is m by 2 V naught square. Therefore, that is equal to m by 2 V naught is 5gl. V naught square is 5gl. Therefore, solving for VB, we get VB square is equal to GL common 5 minus 2, that is equal to 3GL. Therefore, VB, velocity at B, is equals square root of 3GL. Now, to find the ratio of KB to KC, we will divide the energies half m into VB square divided by half m into VC square. So we are taking the ratio of only kinetic energy. Therefore, VB square divided by half m in the numerator and denominator get cancelled. We get VB square by VC square. That is equal to, we know that VB square is 3GL and VC square is GL. That is from equation 3. Therefore, the ratio is 3GL by GL, that is equal to 3. That is the answer. At point C, the string becomes slack and the velocity of the bob is horizontal and to the left. If the connecting string is cut at this point, that is at the point C, at that instant, the bob will execute a projectile motion with a horizontal projection akin to the rock kicked horizontally from the edge of a cliff. Otherwise, the bob will continue on its circular path and complete its revolution. With this, we conclude our discussions on work, energy and power, section 6.5 to 6.8. In the next lecture, we will take up sections 6.9 to 6.12. Till then, goodbye. Thank you.